Hello, everyone. I'm Anup Churian. I'm a research scientist at MERL, and today I'm going to present our work on representation learning using adversarially-contrastive optimal transport. This is joint work with Chuchin Aaron, who is an associate professor at Tufts University. So this is our problem setup. We assume we are given a set of video sequences and that there is an action label associated with each video sequence. The problem we are looking at is to learn to classify each video sequence against its respective action label. Our problem is motivated by the observation that directly learning sequence-level classifiers, such as, for example, LSTMs, seldom works for video sequences. This is perhaps because of the spatio-temporal semantic complexity of this data modality. Usually a deep learning model is trained for frame-level predictions, and such predictions are then agglomerated via, say, average pooling to generate video-level predictions. In this work, we propose a representation learning framework that produces a sequence-level representation, which is very rich, and that can be used in a lightweight sequence classifier for better recognition. More formally, suppose uppercase X represents a video sequence, and say little x1, x2 up to xn are, say, deep features extracted from every frame of the video sequence. Note that we assume the deep learning framework is trained to predict the action label for every frame, but not at the sequence level, which can be computationally challenging. These features are input to our representation learning pipeline. We assume this representation learning loss, denoted LR in the picture, produces a representation U as its output. This representation U, which we assume is a compact spatio-temporal embedding of the entire sequence, is then input to the sequence classifier, which is then trained to minimize a loss denoted LC against the action label LI. In this paper, we assume that the representation learning objective and the classifier learning objective are separate. However, this is just a technicality, and it could be changed to be trained end-to-end in a deep learning manner. The key framework that we base our work is the idea of contrastive representation learning. Suppose we call our set of video features as positive examples, and let's say we have access to a set of negative examples denoted by. Here, negative examples are defined as those that contain only useless information, say with regard to classification. However, the positive examples are a mix of useful features and useless features. Let's consider, for example, in videos, the useless information could be just background motions, while the useful information could be the movements of a person in the video, which characterizes what the action of that person is. So that corresponds to the useful information. The key idea in contrastive learning is to find the representation that is very close to the positive examples, however, is far away from the negative examples. How is this representation used for video representation learning? The idea is that the frame level features X that our deep neural network produces, we assume consist of data subspaces that contain action dynamics. However, as these networks are trained only on individual frames, they cannot discriminate such subspaces. To this end, our idea is to construct the negative example such that we prune away several subspaces that the classifier thinks are useless for recognition and focus our representation, the temporal representation learning, only those subspaces that may contain useful features. In the figure, we assume the useful information is perhaps, say, the different shades of red in X. If we construct the negative examples without red, then contrastive learning will produce a representation that is focused on the dimension corresponding to red, and we can use a temporal representation learning setup that learns the gradual dynamics in the color red across the frame level features. And that's essentially the idea that we are proposing using the contrastive representation learning framework. Now, several questions arise in building such a contrastive learning framework. The first question could be like, how should we characterize the contrastiveness? The second question is like, how can we find the negative examples? The third question can be, how can we capture the temporal dynamics in the positive examples? And how should we represent the sequences? Let's consider the first question. That is, how should we capture the contrastiveness? What metric should we use to quantify closeness or farness of positive and negative examples? Let us consider the sets of positive and negative features. Given that these are set level features in this setting, one possible way to define a distance between the two sets is to treat them as feature distributions. For example, to be specific, we assume that our set X does not contain any temporal information for now, and these are just a random distribution of features, sets of features, or it's a set of features. So let's say mu X and mu Y are empirical distributions produced on the support of these features. If C of xy denote a cost of moving a feature x from mu x to a feature y in mu y, then a distance between the two sets is a total distance corresponding to the minimal coupling between the two sets, which is commonly referred to as the Wasserstein distance. Thus, our contrastive representation learning between the two sets then correspond to finding a functional FU that acts on the distribution of x such that it pushes x far away from the distribution on y. In our setup, we assume Fu is equal to UU transpose, which is a projection operator, where U belongs to the Grassmann manifold. That is, it's a tall orthonormal matrix. This is because the features X are assumed to be the outputs from the last layers of a deep neural network, which is typically used in a linear layer for producing logics. So our assumption on U, which is a linear subspace, is thus justified. We assume that there are these subspaces in X that are characterized by U that consist of the useful information. Through the Wasserstein distance, we try to find the minimum coupling or alignment between X and Y, and then find the subspace U that maximizes this distance. Now, our second question is how to produce negative examples or the distribution of negative features. So we propose to use an adversarial generator for this purpose. What does that mean? This is a framework that we are proposing. Our key idea is to produce a negative distribution as conditioned on the positive examples. However, is generated in an adversarial way. That is, suppose x bar is the mean of the positive examples. Then a sample z from a normal distribution with mean x bar, when passed through a generator g theta, produces an x hat, say. We assume that this x hat, when combined with x, will misclassify x. That is, if the original x has a class label, say flap, then when we add x hat to x, then the same classifier will say the label is not flap. That is how the adversarial nature of this distribution is produced. The classifier fooling is achieved via this part of the objective, where we denote zeta as a frame level classifier and Lx is the true class label of that classifier at the frame level. However, we do not want our adversarial feature y to be very different from the original distribution in X. This is because otherwise any random noise will be able to achieve this classifier fooling without regard to the useful data subspaces. Thus, we use a Wasserstein GAN critic or discriminator that ensures the distributions of X and Y are very near to each other. This is characterized via the dual formulation of L1 Wasserstein distance. Finally, we also want our generated noise to be of the minimal strength. This is achieved via this part of the objective. Thus, our full formulation produces negative examples conditioned on the provided positive examples. Our negative examples are produced in such a way that it does not contain any information that the classifier thinks is important for recognition. Further, using an adversarial distribution generator allows for sampling as many negative examples as we want, irrespective of the number of frames in the positive set. Now, our next question is how can we characterize our temporal ordering within the set X? For this, we use a previous method for temporal order embedding. termed generalized rank pooling. The key idea is to embed the temporal order within the subspace U such that the projections of each feature in X onto U has a distance that captures the temporal order. For example, the projection of, say, the feature xt plus 1 onto U goes into a sphere that has a larger radii than that for the projection of xt onto U. Thus, the U that is produced implicitly captures the temporal ordering in the sequence. Now, our final question is: what is the representation that we want to want as the output of this entire framework? We propose to use the low-rank subspace U itself as a sequence representation. That why is that, or how is that possible? Note that U is specific to every video sequence. It fits to the useful subspaces in X and also embeds the temporal ordering in the sequence. Thus, we can use it as a sequence representation. Given that U is a subspace, we can use a subspace kernel classifier to train for action recognition using such subspaces produced from the sequences in our dataset. Now, putting it all together, this is our full pipeline for video representation learning, which we call adversarially-contrastive optimal transport. We note that we also incorporate a distortion penalty in the spirit of principal components analysis to regularize our representation so that the contrastive setup will not produce features that are very far from the input data itself, thus limiting how much contrastiveness are we expecting. We use a Riemannian conjugate gradient and inexact proximal optimal transport for solving our objective in a block coordinate descent setup. It usually converges in about 5 iterations. Now let us look at some experiments. Here we show how the adversarial noise that our generator produces looks like. We show it on CIFAR 10 images rather than on videos so that we can avoid temporal understanding in our visualizations. We see that the noise is very targeted and is concentrated on regions of the image that is perhaps most useful for recognizing the image category. For example, the face of the cat at the top right. We also present experiments on 2 video sequence classification datasets, namely JHMDB, which consists of about 900 sequences, and HMDB, consisting of about 6,000 sequences. We use VGG and pre-trained I3D features to represent the sequences at the frame level or at short clip level. Here we present an ablative study of the various modules in our setup. We see that using random noise instead of adversarially generated noise leads to significantly poor performance consistently on all the datasets and features. We also find that using optimal transport is useful against not using it. We find that our full performance is significantly better than average pooling performance on both the datasets. Here we visualize the TSNE embeddings. The little circles are the original data features and the crosses are negative samples. As is clear, the negatives are very close to the positives. Average pooling shown on the right shows the features that overlap in several classes. Using random noise to contrast against also does not lead to good contrastive features in our setup. However, when using our adversarial contrastive learning framework, we see significant separation between the clusters, which explains why we get good performances. We also compare our method to state-of-the-art methods on the 2 datasets, specifically on the feature configurations that we use in our setup. We see gains, especially on the JHMDB dataset. Our running time is not substantial, but can work at 30 frames per second in Python and a single CPU if we exclude the extraction time that typically uses a GPU. So to conclude, we proposed a novel framework for video representation learning by combining contrastive learning, adversarial distribution learning through GANs, and optimal transport. We used a Riemannian optimization framework to learn subspace representations. Our experiments demonstrate that using adversarially produced negative examples to contrast against leads to significant performance benefits. Our code will be available very soon at this provided website. Thank you so much.